do in this lecture is, so imagine you have a random landscape, as we always picture them. There are 2 points of view.
Sorry, just one thing. The black pen are the one that work best.
Okay.
Oui.
So what is the line of
Maybe more, not
lower or? Okay. So what I'm going to do is the extreme physicist point of view. From now onward, if you can recognize the objects as being the same in my talk and those of Gerard, it means that you have a deep understanding. You can notice that they are the same, when they are the same. Okay, so when one studies random landscapes, there are 2 basic approaches. One is, let's say, topographic. You want to know where are your minima or your attractors, and then you say, okay, I have these attractors, they are separated by barriers, and then you do like this, let's say, topography, without asking much how you got there. So, for example, the most typical example and the initial one for spin glasses, which were perhaps the first thing to be studied really in detail, is to look for the ground state. Of course, this is clearly a topographic thing. You're allowed to say, I want to know what is the ground state, but of course, you're not saying how you got there, or that's the static or topographic approach. And then comes another way, which is, in the case of spin glasses, or in the case of glasses, is to say, okay, but I never get there. A glass never gets to equilibrium, and a glass is a glass because it is out of equilibrium. It's not what it does, but it is what it is, a glass. So this kind of approach is dynamics, where you discuss what happens with a trajectory, a typical trajectory, or an algorithm. Dynamics is just one algorithm, but you could study the exact dynamics or the typical dynamics of an algorithm that you like. And I'm going to give you one example at least in such a landscape. So you have this, you have this. Of course, if times are sufficiently long, you will eventually get to the ground state. So these approaches, of course, are not unrelated. Then this is a dialectic relation between these 2 approaches, because then you will see that statics or topography, if you want, strikes back. Because when you study dynamics, you realize that, for example, in some cases you have many minima, but from dynamics you find out that you go grazing in the highest ones. This is something that you need dynamics to tell you. Nothing else can tell you. But once you know it, then you can apply the topography, because this is, once you know that the highest ones are the relevant ones, now this you can calculate with pure topography. And furthermore, you will see that at least in mean field, you visit them democratically, completely democratically, which is an enormous surprise, and I don't quite understand it yet. But this flatness of the measure also gives you an extra interest in doing pure topography. So this is why I say it's a dialectic relation, because you give up pure topography for dynamics, but then dynamics teaches you something that revitalizes the topographic approach. But of course, you're no longer looking for the ground state, you're looking for something else. But then, when you think of it, you don't want minima. You normally you have some stochasticity. So actually you are moving around. And in fact, what you would like to know is this pocket of probability, which in physics we call a state. Or if you have a SAT problem, I'm going to define them later, a constraint satisfaction, these are the states that you're interested in. But those that are connected, you want to identify them as a single lump, because it's not hard to go from one to the other. So how are you going to define this? How am I going to count? How am I going to do Gerard's calculations, but for states and not now for points? So I want to do topography, and then I realized that in order to define these guys properly, I have to do, again, dynamics. And you will see that there is a procedure whereby doing dynamics, you can define, count, etc., the states. And this has been underexplored in this subject, but it is very interesting, I think. Of course, so you see that things fight back. On top of it, when you want to do topography, there is a kind of relations, topological relations, which is called Morse theory. I'll give you the first and clearest result in Morse theory. If you have a potential that is like this, that goes to infinity, you see that the number of minima minus the number of maxima has to give 1. Okay, this is a bit stupid, as it is, but when you do this in many dimensions, etc., it's not so stupid, it's even very beautiful. And this tells you all the constraints about minima, saddles, maxima, etc. When you want to study, this is the most topographic thing that you can think of. When you want to study and do an intelligent, clever, and two-line proof of this, then you discover that it's going back to dynamics, the quickest and easiest way to do it. I'm going to hint at a proof. Yeah?
Maybe you're going to say it. I just was wondering what the conditions are for this level.
Oh, okay, so if these go to infinity and the function is relatively decent, you see that it's almost a counting thing, no? You have
I meant in like multi-dimensions.
Oh, yeah. I'm going to say what it becomes, yeah. And this is a very beautiful, very, very beautiful work, which I'm only going to just mention because it's I think, lovely, by Witten in the 90s, and where he derives all these things like this using Langevin kind processes. So you see that this is a back and forth between the two things. And one thing that is almost opposite to the other, I started out reading Professor Sumpolinsky's paper and being a complete convert to dynamics from the beginning, and yet you have to admit that once dynamics teaches you something, dialectically the topographic approach can fight back, which is the case, for example, when you have a situation where then you discover that you can do a static calculation. Okay, so this is where I'm going to go back and forth. One of my main points I want to repeat as many times as I can, but already Gerard did his dose of it, so you will get a double dose of it, is high dimensional landscapes are not like this. I will keep on, in at least 4 occasions, doing drawings like this, and then showing you how wrong they are when you want to think of a landscape in high dimensions. This is a disease that affects a lot of theoretical physics, especially to do problems in 1 or 2 degrees of freedom because you understand them, and then discovering that what a thing that has many degrees of freedom does is nothing to do. Just to give you the simplest example, imagine you have a species of anything, us. If we were 10 in the world, of course, there's a chance that a tree will fall on each one of us, and to the 10th power, it gives you the probability that 10 trees are going to kill us 10, and then our species is dead. Any species that is small is inevitably going to die this way. And in fact, this is why you cannot have a small natural park and expect to have pumas inside, because you can have 4 pumas because they need a lot, and then one dies of natural death, the other dies of sadness, and then so even biology needs large numbers, because you need that. This gives you a barrier for death, that without which there would be no nothing. So even this needs a dynamics with large numbers. I don't know if anybody's going to tell stories about ecology and landscapes here, unfortunately, because that's a nice. Okay, so I'm going to insist ad nauseam really about large dimensionality, because this is really, really very important. Okay, so examples. So one example you probably all heard about is the easing model, but whenever there are spins that are plus minus 1, we don't like them because the landscape becomes discontinuous, so we make them soft. So making them soft, for example, could be having a field that depends on x. This term wants the field to be as constant as possible, and instead of plus and minus 1, I use a function that mimics this with a big number here. So this is a field that prefers plus minus 1 because of this locally, and then prefers to be constant. So this is a model for this energy for a ferromagnet. And I'm going to not use this one, but the ground state for this one is gradient phi equals 0 and phi equals plus or minus 1 everywhere. So just to show you the first drawing you shouldn't do is this, saying that this is a ferromagnet that can be globally up, meaning that the thing is magnetized up, or globally down. Okay? And why you shouldn't do this drawing, I will tell you in a while. Okay, but this one is too difficult, so let us well, before going on, let me tell you what happens with this system when you produce it. I have a picture. Wait a second. Okay. So black is minus 1, white is 1, and you start in a very disordered way with the phi's, and then it has to decide whether it wants to be all black or all white, okay, because of this. This is what really a ferromagnet does. And as time passes, it tries to decide. Whites want to be with whites, black want to be with white. The boundaries are not, the system doesn't like them because they cost energy, and this process happens, which is called domain growth, and after a time, which diverges with the size, the system becomes all black or all white. Okay? And if you have non-zero temperature, then other things can happen later. Okay, so, well, I can tell you right away why this picture is bad, because you think that when you have a double well, you start here, and doink, you fall there. And now you notice that falling into one of the two states is much, much more complicated than what you thought. And not only that, it takes a time that becomes infinite when you have infinite size. No, because these grow, they don't care about the size until they conquer the whole continent, and if the continent is infinite, it takes infinite times. Mm-hmm. In fact, it takes this length squared. Okay. So this model does this very well. You can put it in the computer. It's easy to simulate. Okay, and wait, I don't want to mix my pages. Okay, so a model that is easier to do, and it's basically the same thing, is take a grid in. I'm going to choose 3 dimensions, and do this. Put a phi in every point, okay? And, well, discretize this, so it's I, j plus 1, k, minus phi I j k. This is one of the derivatives plus phi I plus 1 j k squared plus, okay, okay. So this is the discretization of this. And then Berlin and Katz realized in 1952 that if you wanted to make this problem easy, rather than have this nasty quartic, you see, quartic thing, which is going to make your life miserable, you could do it just by doing this very strange thing. I'm doing it in 3 dimensions, but doesn't matter. So instead, it's very bizarre, no? Instead of making every phi plus minus 1 or something that resembles plus minus 1, they chose a global constraint, which is a bit bizarre. So now we are on the sphere that Gerard loves, and for good reason, because this is now much, much easier to solve, okay? Because it's just a quadratic form on a sphere. And how do you do this? Well, I'm not going to tell you now, but you have to diagonalize this quadratic form, and you will find that, leave it for later.
Yes, question.
Yes.
So it said that this is nice because you get rid of the quartic term, right?
Yeah.
So how is this equivalent to?
No, at the end of the day, it is not really equivalent, but it is also a good model for ferromagnetism.
Nice.
Okay, so it's not that this one and this one are identical, but they do have domain growth, ordering, etc. Because these, of course, you want to make this term small, and so, okay. But equivalent, no, they are not. In fact, this one, there's no way. I mean, if you want to do the dynamics of this, you cannot solve it like this. It's the picture over there. Okay. So now let me continue with my collection of models. So keep this one in mind, please, because I'm going to come back to it in a short while. So this one we will keep in mind, but for the moment we are not going to do much with it. So I suppose you already saw in these lectures of spin glass, the model, the canonical model of a spin glass in any dimension is you take random couplings, typically independent, and you build yourself an energy with NN means nearest neighbors. This is called the Edward Anderson model. Of course, there is no hope at all to solve this in finite dimensions. The most you can do is simulate. Okay? That's how things are, and they will be, I suppose, for a long time. But then Sherrington and Kirkpatrick, probably some Edwards, I don't know, decided that, of course, you have to try to do a model that is simpler, and the classical strategy is to do mean field. Oh, sorry, these are plus minus 1, okay? So, in order to do things easier, yes, stop me all the times you, yes. No,
This model, of course, is, at least from a mathematical point of view, hopeless, but there is
and physics too.
there is a little bit of cramped progress on it,
Of existence and things like that.
of what happens for the
Yeah.
but,
But-
dimension 2.
Okay, but still, it's interesting. I mean, it doesn't have a transition, but it's nice. No, this is tough, really tough from any point of view, physics, maths, whatever. So, okay, so Sherrington and Kirkpatrick, what they did, I'm following Gerard's notation, not the usual one in physics. I saw it this morning, I thought it was better. So with the J's with variance 1, they did this, but everybody all with all. This is what you do when you do mean field, okay? Because you expect that when it's everybody with everybody, then it's going to be easy because you feel the field that is an average of everybody, etc., etc., etc. Turns out that even that is the solution of Sherrington-Kilpatrick, exists in physics, and it's one of the most admirable tour de force that we've all come across by Parisi. And then maths followed, and another extensive tour de force. Now we know that this is right, but not retracing Parisi, bizarrely enough, doing it with a method that is similar, but inspired, but not it. Okay, and now a thing that happened that was, so yesterday I reconstructed. I think that the first to mention it was Bernard Derrida, then it was used by Gross and Mézard, then an important paper is by Gross, Cantor, and Sopolinsky, and then Gardner, is because it's interesting to study with the notations à la Gérard, but with plus minus 1. Okay? And this is, bizarrely enough, for p larger than 2, it's simpler than this one, but not very simple. And in fact, the dynamics of either one has a lot of tricks. But then somebody remembered what Berlin and Katz had done, and this was Crisanti and Somers, and they decided that these you could do with a spherical constraint, which is, instead of imposing it that each one is plus minus 1, you impose it for the sum. Why did they feel that this was easier? Because it's easier to treat in every possible treatment a term like this one than a term like this one, or its quartic cousin that I did before. So it was a good idea technically, and you hope that this doesn't have a big effect. Well, for p equals 2, it does have a big defect. It trivializes a lot the model. So Sherrington-Kilpatrick, which is the name of this one, is much, much more complicated than its spherical cousin. Yet this one is interesting. It's interesting. And this one is much easier to treat in the spherical, and here you don't lose much by making it spherical. But this is a complicated trick, because now you could, be a bit courageous and say, well, why don't I do Edwards Anderson with a spherical constraint? That would be great. I can do it exactly what Berlin and Katz did for the ferromagnet. I do it for Edwards and Anderson, and it doesn't work because maybe I'll tell you in a second, but what happens is that you end up with a quadratic form. Yes?
In what precise way does it not work? Because since analytically we don't know anything about the Edwards-Anderson model, so it's so hard.
I'll tell you. Why doesn't it work? There's a good reason that this works, because phi ijk, when you solve it, all of them are of order 1. So they are a bit like, they're not plus minus 1, but they stay order 1. If you do it for Edward Anderson, and you want to solve it, what you discover is that you get a very long spin of length n and very little away, and that's not a model of anything.
That's true for also large p, or only for p equals 2?
I don't know. In finite dimensions, I don't know. And there's another thing I don't know, is if you could twitch a bit this randomness in order. I don't know. But if you try, well, that's an interesting story in itself. Only to say that you cannot make anything spherical and get away with it. Sometimes it works, sometimes it doesn't.
Okay, this is,
Yes.
I've never heard of this, but the spherical, the way you make it spherical, the Edwards Anderson,
Yeah.
is it just the neighbors?
No, all. And when you try to do it and try to be smart and have a 3D thing that you can solve, you discover that you cannot. That you can, but what the result you get is irrelevant to anything. Okay, there's also nice things that one can do even in that case, but that's another story. Okay, so now let us concentrate for a second on this one, on the spherical versions. I told you that, well, this one you've seen a lot with Gerard, but I'm going to repeat. I'm going to repeat a lot, in fact. This one you forget. And now, okay, let us look at this one. So what do we have? We have a quadratic form on the sphere. Okay? On the sphere, because we are on the sphere. Here too we have a quadratic form on the sphere. Okay, when we diagonalize this quadratic form, you know what we get. We get this famous semicircle, which was drawn many times. And these are the eigenvalues of the J. Now, how do you diagonalize this quadratic form? Well, it's not hard. In one dimension, what you would do is you would say that phi I is just essentially by discrete Fourier transform. Sorry, I won't use A because. So, well, I did it in one dimension, but you see how it goes in many. And the eigenvalues are k squared. And k goes from minus L to
Sorry,
yeah.
in these models you said all means fully connected. And
Yeah, yeah.
So where is space gone? And
Here there is no space.
right, so it,
I killed it because I wanted to be mean field.
but then you said something about finite dimension. I mean, that you were commenting them as if they were finite dimension.
No. Edward Anderson, that was
Edward
here, is the one that you cannot make it spherical. Okay? So, okay,
Another
this.
question.
Yeah, sorry.
So in another translational invariant system, how does the Fourier transform?
Oh, wait,
Fourier
this is
transform
translational invariance. It's a ferromagnet.
Okay. Fourier transform.
Yeah.
Okay.
This one you can diagonalize because it's a random matrix, no space. Now, a miracle happens that you can check just by doing this calculation, that when you look at the spectrum of this matrix, it's this. And when you look at the spectrum of the matrix that corresponds to this quadratic form, it looks in 3 dimensions, it looks density-wise exactly the same. So the important part is that this goes like lambda minus lambda min to the 1/2, and this one goes the same in 3 dimensions.
What?
Hmm?
In what dimension?
3. So in 3 dimensions, by a miracle of life, this model that has no space and that you decided to put on the sphere because you need for technical reasons, has essentially the same spectrum as this one. And this one is supposed to mimic a disordered system and without space, and this is a not disordered system, just a ferromagnet in 3 dimensions. Now, for one of these miracles of mathematics, essentially the density, or not the details of the statistics, but the density of levels is the same here and here.
You're talking about the SK model?
Spherical.
Spherical SK.
Yeah. Yeah. It's important that it's spherical. So both models, Berlin-Katz in 3 dimensions, which is a ferromagnet, and you have to think more or less in these terms, and the P equals 2, which is, it was born as a thin glass, and then we did some, two at least steps. We made fully connected interactions, and we did a spherical constraint. By a miracle of mathematics, when you solve this one, you essentially also solved that one. So, so how does this one look? How does the energy look? Well, that's not hard, no? You have a sphere in n dimensions, and then you have a rugby ball, essentially. If I'm going to draw this potential, it's an ellipsoid with the smallest energy corresponds to the smallest eigenvalue, and so on. So you see it's a quadratic form on a sphere, so this is a rugby ball, and you have all these directions. And in fact, the lowest eigenvalue will correspond to the ground state, which you have 2, and then you have all. And this one is exactly the same, only that this spectrum is labeled by the energy, which is k squared. K is k. the k of the Fourier transform of this one. So this one here for that is the lowest eigenvalue that corresponds to k equals 0, meaning that it's a flat constant. It's a ground state, they're all pointing in the same direction. And then you have more, but because of the discretization, when you are asking for the degeneracy makes this low. Okay? If you want to calculate this, it's simple. You just have to look, you have this grid of k's, and you have a cube, and then you cut it in slices of k squared, and then when you count the number, it reproduces this curve. But it doesn't matter. Okay, so the important part of this is that when we discuss or when we solve this model, by miracles of life, we are also learning something about that one. What is the advantage of this one? That we know a lot of things and that is related and it's with mean field, but the advantage of that one is that we can have an image of space, of real space. Okay? That's okay. And now, what about, oh, sorry. And now you, let me do the B-spin. This one, now this one is different. If I had to make this picture here, of course there's nothing like diagonalizing a tensor. There is no notion or no possibility of writing this in a trivial way. That is what you do when you diagonalize this. So, but that's a technical or a fact of life, but if I drew this function, it would look like this. So it has many minima of various heights, and this is what Gerard was describing quite a lot. So it has, and we will, of course, come back a lot to this. This model is a model that allows you to do with relative simplicity things that would be much harder otherwise. It is sufficiently complex that you can do a lot of things. For any p larger than 2, it has many states, an exponential number of states, and you can go. It's the cheapest if you want. Thanks to the Berlin-Katz idea, this is much easier than this same model with plus and minus 1, which is what Chaim studied years ago. Here you gain a lot in ease of calculation. Okay. Maybe I want to say one little thing, is that immediately we can, I don't know if Gerard did this, but for both, we can estimate, because they have the same spectrum, the calculation is exactly the same, what is the height of the first barrier between the two ground states. So, for example, in this case, you have them all aligned, and you want to go from one to another, and you want to know, or here, you want to know what is the distance between the two. So it's very simple. This is the ground state aligned with this one. It's when lambda is the index of ground state. I don't know if I am using, I rotate to the basis where it's diagonal, and then, and it's okay, and I look at the difference in energies between the lowest possibility and the one that follows. So the calculation I have to do is integrate the density between, let's say, 0, I'm taking here, and I'm looking, when will I find the first? So I go from 0 to the first eigenvalue, and I am integrating, I told you that the tail goes like lambda to the 1/2, and I want to catch the first one, so I have to put that this is equal to 1/n, because this is a density. And when you do this, well, this gives you so that the total energy barrier is, the total energy barrier is n to the n to the, sorry, 1/3. Here and when I have something that is extensive, that it is a sum over all the space, I use capital letters for energy, for example, and for energy divided by the size, by the number, I use small letters. So, what does that mean? It means that the barrier, for example, if I have a ferromagnet, the barrier for going in this model, for going from one state to another is, or the barrier here to go from one ground state to another is n scales like n to the 1/3. So you see it's very low because the system's energy is order n. And in this model, the barrier to go from one to the other doesn't even, if I look at it from the point of view of energy density, it would be n to the 1/3 divided by n, and this is a very small number. So,
Can you say something now how you infer this from?
yeah,
How do you infer the height of the barrier? From
I'll come back in a while in all detail. You infer it because you find that the difference in energy, we will do a calculation between the eigenvalue, the two first eigenvalues gives you exactly that, because one corresponds to the energy of the saddle, the other one corresponds to the energy. Well, maybe I do it right away so that I don't generate suspense. You want to find saddle points on the sphere. So you have this is your energy. Yes? But you want it to be a sphere, so I need a Lagrange multiplier to impose that. So I will add a Lagrange multiplier times the sum of these. Okay? So now I take a saddle point, and then I will fix z so that it does the job. So the saddle point is lambda, sorry, I put a minus, but it's conventional, minus z s lambda equals 0. Which means that to satisfy this, what I need to do is choose all the z lambdas equals 0 except one. And for that eigendirection, z, I fix it to j lambda.
Why except one?
You could do because that's the one that gives you z s lambda squared equals n. So the axes of this rugby ball are the eigenvalues, and the lowest eigenvalue corresponds to the energy, because you can read it here, that it's the lowest and the next. Okay, so the fact that between, let me give you another example, perhaps you will see it more clearly. It's in the other example of domain growth of ferromagnet that I gave, all the phi's positive is one ground state, all the phi's negative is the other. When I want to go from this one to this one, the passage point, you can believe me, is the highest point is when I pay the most, is I start growing a bubble of this, and when this bubble is half, this is the most expensive thing. So how much do I pay? Well, I pay this cut surface when there is an interface that I'm paying in energy. And when you see this energy I'm spending is small compared to the volume of the system, it is one dimension less. So this means that the barrier from one state to the other, and now picture number 2, is that when I have this barrier here, this barrier is not an order of the size of the system, but it's smaller. It's n to some power that is smaller than the size of the system. So one thing that we will see in a while is that when I make a drawing like this, I am cheating, because the actual energy that I have, even at low temperature, is enormous compared to the barrier, and still I don't go to the other side. So this is important because it shows again that this picture is misleading. For some reason, the useful energy that I have does not allow me to jump this particular barrier, which is the one I would like, even though I have lots of energy, but somehow it doesn't herd in the right direction, and it never happens for a large system. So that's picture number 2 to bear in mind that where thing might mislead you. Okay, so those are the only examples I'm going to do. So about the p-spin, the one that I just erased, I will repeat, we will come back to this, but maybe it's good to repeat it now. It's things that Gerard said this morning also. You have this potential, this energy, sorry, and when you look at the minima you have, this is just a symbolic picture, it doesn't mean anything. You have a lot of minima, then you have less, then you have less. You have an exponential number until you have a lower one. And above a certain level of energy, you don't have any local minima, and you only have saddles. Okay? So if I cut a slice here, and because all my energy has is saddles, my energy is connected. The only way an energy can be disconnected is if you have two minima and you're cutting a slice. If I have like this and I cut a slice, I disconnect. But if I only have saddles, well, and I cut a slice, this will never disconnect into regions. So above this level, the whole landscape is connected, and below this level, it disconnects. And this was mentioned perhaps in a slightly different language by Gerard, but this level, this is why it's called threshold, because it's a threshold between a percolation threshold where all of a sudden the whole landscape becomes disconnected. Okay, one other landscape that I'm going to put in relation with this, because this was talks on high-dimensional landscapes, are constraint satisfaction problems. Did anybody talk about constraint satisfaction problems here? No? Bézard. Okay. Okay. So constraint satisfaction problems. Okay. Okay. Let me give you some examples. So one typical is packing. You have spheres of size, hard spheres of size r, 0. You put them, constraint satisfaction means put as many as you can without making an overlap. Okay? The constraint is you don't want overlap of spheres, and you put, so you're satisfying the constraint of no overlap, and you're putting all these spheres inside. Another, probably this one is the one that Mark mentioned, is if you have a graph with average connectivity C, and now you have a number Q of colors, and you assign, for example, red here, but the rule of the game is that you are not allowed to put the same color into contiguous fields. So red, here you put blue, and the rule is that you are given Q colors and you want to color this graph. So the constraint here is the law that forbids putting two colors together. And yet another constraint satisfaction problem is what is called SAT. So you have a Boolean expression where you're asked to satisfy M statements, Boolean statements, and now each statement is, you have Boolean variables Z, and each statement is a set of, you choose, for example, 3, and you want this OR, and then this would be C1, And then you have another statement, you take them randomly, which could be that. Etc. So you have a lot of statements which you want your Z to satisfy all of them, in this case all M of them. And the question is, can you find a solution that does it? So you see, the three problems have in common that you have a series of restrictions that you have to respect, and you are trying to find if your state, if your ensemble of possibility, there are some that respect all of them. Okay? So what is the connection with landscape? Well, there are two connections. One is the usual one. You could, for example, in this case, call energy number of violations. So it's number of, you assign colors to your vertices, and if I had this one, this red with red is bad, so I count it as 1 in energy. So it's a number of errors basically I make. So, and if you call this energy, then the question would be minimize your energy and try to get to a point where there are no violations, and that means energy equals 0. Is this okay? Okay, that's the standard way. Here, the same. You could call energy an overlap, you make it pay in energy, and so you would, for example, count the number of overlaps. Now let me give you a different one that I think it is useful to make a better connection, or at least to make a useful connection between constraint satisfaction and the landscapes. So imagine that, let's take this one. Our space is all the x's of all the particles, okay? So here I choose a particle, and what's going to later be my energy is the common radius R0, which they all have. And so I start with this point, and I start with 0 radius. So I'm sure that my configuration is okay. Okay, because they have no radius. And now I start growing, keeping the configuration the same. I start growing, making the problem harder, and there will come a point where this configuration no longer works, because with this configuration, two spheres at this radius are touching. Okay?
Sorry, so we have lots of spheres, and we increase the radius of all the spheres
Simultaneously, yes. Without, for this configuration, changing anything. Okay? So anything growing more than this is not allowed. Clearly, it's going to be even worse. You agree with me? We're going to inflate even more. For the point next to it, this could be another level at which the whole thing spawns. I move the spheres, and well, I could inflate maybe a little bit more. And for this other configuration, I can only inflate a bit less. And for a configuration that started with 2 nearby points, immediately it will be violated. So now let me reconstruct the function of the first time that my constraint is violated. And I will get a function that is going to be quite ugly, but it is a function that tells you how far I can go in R0 until I violate. And you see that this function exists, because at each point there is only one point where it begins not to work, and if you continue, it will continue not to work. Okay? And so, so in fact, in this case, it's very easy. The function is the minima of R0 equals the minimum of all the Rij, no? Because that's the one where it fails for the first time. So what is the advantage of this? The advantage is that I didn't add anything to the problem. I didn't allow for overlaps, which I don't want. And I am studying the constraint satisfaction problem just in itself. And you will see that you can assign a meaning of moving in a gradient, along a gradient on this landscape. and you can assign a meaning to what is a barrier, and you can inspire a lot of the things you know from ordinary landscapes and translate them to these constraint satisfaction problems. This is just a little dictionary that you can use. For example, if you know how to do a Monte Carlo program for a landscape, then you know how to do a Monte Carlo program for this. If you know what a threshold means, this level of highest state for a landscape, you can expect that you're going to have something similar here. So this is not particularly the solution of anything, but it gives you an idea that constraint satisfaction problems, when looked from this point of view, are basically the same as are a part of a landscape. So it's just a construction, it's not particular. For the coloring problem, what you are adding is you can start with no links. The number of colors you keep. But now you add links to the problem, one by one. You have a list of links and you add them one by one. When you add a link, it can only make life worse. It cannot make it better. So there will be a first time where every possible configuration which you kept fixed, just like you did here, there will be a first number of links where it will fail. That's going to be the level function. You will see that to do the analog of a gradient descent here already is an excellent program, really excellent. It works better than belief propagation, for example. So,
and in this case, you define this on average, don't you? Because the way you choose the link you are...
When they are random, you have to construct your list, and you're obliged to pick them one by one, and you're not allowed to change your list. That's a subtle point, but it's important. Yes, absolutely. Okay, so I'm only telling you this because I want you to keep this in mind, because I will show you how you can, by analogy, understand things that happen in constraint satisfaction just from what you learn that you think are generic things of high-dimensional landscapes. Okay, so now please, I don't know if I'm saying things that are trivial or not to you, so please, if they're not, stop me, and if they are, tell me to hurry up. Okay, so a small, I'm going to, I know that you've seen a lot of large deviation functions and large deviation principles. I would like to go through this in the language of a pure physicist, so very, very careless arguments, but those are the ones that usually you can inspire at least to try to know what would you like to prove. So I think that most of you are physicists. When you study physics in undergrad, you want to know, for example, what about the energy? How does the energy of a system scale? So what they tell you is, well, I'm at a temperature T, and then I cut my system into two parts, and let us assume that our system doesn't have long-range interactions, that everything is more or less reasonable, the forces. So you say, okay, so it means that these two systems, essentially the energy is going to be E1 plus E2. And with this argument, they convince you that you know that the energy roughly is extensive. Then, to prove it is another business, but you all swallowed this at some time in the beginning of your career. So, for the partition function, you do something similar, but now you discover that, well, it's something like, if I do the same argument, so that this, energies of the system 1 and energies of the system 2, and this is how you say, okay, the partition function is not like the energy, it goes like the product. So in this system where I put many pieces together, when I put many pieces together here, I would be, if I cut it in many, many pieces, this would be, that this implies that Z will go to the power of the number of pieces, and this is why you expect it to scale like an n outside. So, okay, and because you can take a log, because the free energy is minus the log of the partition function, the free energy instead is extensive, it's the sum of that of two systems. Okay? You all were told this, and if you were like me, you accepted it easily, although of course this is not a theorem. Okay? So now, good, but now, and for deviation, you would say, well, the probability of having a certain energy, now I cut in many pieces of fixed size, but many, and the size is fixed, but the number of these pieces is going to scale with the size of the system. So the probability of this, if I consider that it is a product of the probabilities, then it will be something like e to, there are n of these, and then the probability of one single one of them, which will have an energy, it's a little piece, like this. And this is how you get, of course, I am neglecting a lot of interfaces, but this is how they told you to think. Well, for large deviations, you didn't get it in the first years of the university, but you more or less reason this way. Okay? You are in finite dimensions, you have interactions that are local, you cut the system and you say, I think in terms of a Cartesian product. It's not really, because this interface is cost, but to a first approximation, I think in terms of a Cartesian product, and that should more or less give me an idea. At least I know that no way it's going to work additivity for the partition function, you see? Because even for a Cartesian product, it is not additive, it's multiplicative. Okay, then you're given later on, you have a glass of water, and you're applying power to this, you're shaking it, and you measure how much power you are, how much energy I am giving to the water. And this is the glass of water is in a thermostat, so let us suppose it doesn't heat up. And this fluctuates. Why? Well, because this might create eddies that go to the boundary, come back, bounce. It's a disaster what's happening inside, so this is a fluctuating quantity, you agree. And also, if this water would be microscopic, there would be molecules individually, bumping and so on. And now you say, well, but this is the integral of the omega being the angular velocity times the torque, the instantaneous torque, dt. Okay, so I'm integrating, this is precisely the instantaneous torque, and this is time. So, okay. So now I ask, and this is a very common question, I'm going to tell you in a second when it appears, what is the probability that I spent during a time t a certain energy, a certain power? Now you do exactly the same thing that you did here. You say, okay, now in time, what I spent up to here, if there are no long time correlations, I can cut my slices of time just like I cut the slices of space here, saying that, okay, for all the future and for all the past, in a system that hasn't got correlations that are abnormally long, I can almost think that this is additive. And following exactly the same arguments, but now the size is not the size, now it's a time, so t, and then here there will be some function of the power, the total power, divided by t. Exactly, so this is the intensive in time power, and this is the large time parameter. It's exactly the same argument that you're using for. So you're saying that the probability is multiplicative. It's the log of the probability that is additive. Now there is a social phenomenon, which is that when you were 20, you accepted easily the additivity. Maybe we all did. And then when you do it in time, no, then you're sent to read Don Scarvaradan, which is beyond me. I'm not saying Don Scarvaradan is a fantastically good literature in mathematics, but it's fair enough. I mean, they did what had to be done to make this hand waving solid. But the thing is that we don't ask the same from space. We, meaning the physicists. We accept the space and we don't give it a thought. But when we're talking about time, then we behave differently. And this is purely social. I'm saying this because...
So it's better to be always cramped.
That's a possibility. That's consistent. That's consistent. What I think is that for historical reason, time distributions were in the hands of mathematical physicists, Galavotti and people like this, who had a sensibility towards this, and somehow it's a ladder and that is missing one rung. For me it's okay, but I mean, you should be aware that between 0 and 2 there is a 1 that you can do, which is the one that you swallowed without any inconvenience when you were 20. So personally, I trust I will die, I hope at least, without having read Don Scarvaradan. I'm pretty sure I will. This is one of the few things I am sure of. But it's not for everybody. I mean, okay. Why is this interesting? It is interesting because the distributions of work are very, have attracted enormous attention, because you can say things about this. I don't know if you've heard about the fluctuation theorems, Galavotti-Cohen, and so on. They are theorems that concern this distribution of work. And there's an immense amount of papers on this quantity, of which, even out of equilibrium, you can say things. There is so little in life that one can say out of equilibrium that already saying something is a lot, and the fluctuation theorems are theorems on this. Okay? But what you have to think is that from the point of view of existence, etc., you can be not cramp. Okay. Another one. Always reasoning exactly the same way with Cartesian products. Imagine you have a system and so this here is the basin of attraction of this, if I'm doing gradient descent, okay? So the basin of attraction is the set of points that under a certain dynamics will go and die where I want. Okay. How does the volume of the basin of attraction scale with the size? I have a system with many basins of attraction. What is the question I have to ask? So as usual, you think of a Cartesian product. So it's very easy. Now you have two systems. This one cross another one. So you have E1 plus E2, and E1 depends on X, E2 depends on Y. They live their own lives. So X1, X dot is minus D1, and Y dot I is equal to minus dE2 dy. Okay? So now let me draw the Cartesian product. This is system number 1 that wants to go here. This is the boundary of the basin, and here it will want to go somewhere else. Okay? And this is system number 2, which has the thing here and has its own basin of attraction. Okay? Now, of course, I think I take the Cartesian product of both systems, and you see what's happening. The product system will go here, and this with this, and the volume of the basin of attraction is clearly the product of the volumes. because to go to the Cartesian product of minima, I need to be in this minimum and in this minimum. And the set of points that takes me to that, if they're independent, is being here, here, and here, here, and that's the product. So, morals of this is that when you're thinking of the distribution, for example, in the p-spin, of volumes of bases of attraction, this volume of the basis of attraction has to scale like E to En log like everything else. Sorry, what am I doing? Some function of the log of E over E, just like everything else. Okay, so we learned something about that, because now this is going to have a big consequence for us in a minute. Of course, all these things I am doing assuming that the Cartesian product is okay. And every model that has fully connected cannot be broken in two. So, even for a physicist, non-mathematical physicist, when you're doing fully connected, you have a moment of hesitation. You really, being that you cannot cut it in two, you have to think a case by case. And there are things, and I'm going to give you a few examples where the things don't work that way. But as a first approximation to the problem, it's useful. Okay, now, sorry, one thing that I did implicitly say here, but I want to say it again. Is it obvious that if I have a product of systems like this that are independent, to be in a global minimum, I need to be both in a minimum of one and in the minimum of the other. So the minima, the number of minima is multiplicative. Okay, so the number of minima has to go like, again, this is called the complexity, usually, and in physics is called the complexity of whatever variables you have. It could be the total, or it could be the one restricted to a given energy. It could be a function of many things, but it has to scale this way. So the fact that you have exponentially many minima in the p-spin is not, after all, so surprising. But you, of course, can tell me, yes, but you are using Cartesian product and breaking the system in two, but you cannot do this with a fully connected p-spin, and I cannot, indeed. But, you know, at least it gives you an idea. For Edward Anderson, a model that is local, you can always cut it in two. Okay, and now let me introduce one quantity that is a lot of fun, although I'm not sure how useful it is. So let me define the following quantity. It's a kind of Cartesian function. It's called a Morse polynomial. And it's defined this way. You count all the minima. So the index of a minima, Gerard, how did you denote the index? I. Great.
K.
K. Okay.
Index
Okay. So, what does this mean? So, it's called the Morse polynomial because you write it like this: the number of minima plus x times the number of saddles of index 1 times x squared, the number of saddles of index 2, plus like this. But for us it's cuter, instead of x, use e to the minus mu, because of a matter of taste. It doesn't change anything. Okay, it's just a way to encode how many saddles of each kind you have. Okay? Mr. Morse, I suppose, liked it because the property I said before is generalized on the sphere saying that P of minus 1 is 0. This you can prove, it's the generalization of what I wrote. But forget it for the moment. This is Morse theory. We will discuss a little bit later. But this is the clever way to encode this.
It's 0 or 2,
Or 2.
depending on the parity of the manifold.
Oh, yeah, no, on the sphere I was.
On the sphere, it's 0 or 2, depending on the dimension.
Okay. So now, a moment of reflection will show you, if I want to have of two independent systems, a saddle of index 1, I can do it in two ways. So we said before that if you want a minimum, you want to be in a minimum of this one and a minimum of this one. If you want to be in a saddle of index 1, do you agree with me that you have to be in a minimum of this one and a saddle of index 1 of this one, or on a saddle of index 1 of this one and a minimum of this one? Because you need one negative direction. A saddle of index 2 is done with 0 and 2, 1 and 1, and 2 and 0. Agree? From this, immediately you conclude that the Morse polynomial of something has to, of a product, has to go like the partition function. When you think of it here, number 1 times number 2, and you conclude that the log of the Morse polynomial is the quantity that you have to look for, because this one is the one that you expect to be additive in a system. I don't know if anybody has mentioned this, but I find it, well, I can tell you one application it has at least. Okay? Okay. So now, one application of this, of all these things, and that it's quite obvious and in fact quite. So when spin glasses started, there were first the works I mentioned before. No, I didn't. Of Stompolinski and Sibelius, to which I'm going to come back, but they were not manifestly out of equilibrium. And why didn't people want to study out of equilibrium analytically? It's because reasonably enough, well, not reasonably in fact, we all thought that this landscape is complicated. I start from a random point. What do I know? It might end up anywhere. No? I mean, how am I going to make a theory of something that is so bizarre as landing on one of the many states of a landscape that is a mess? Well, no, this was our low-dimensional intuition that was cheating us, and you will see now why. So this is again one of the pictures I would like you to bear in mind that you shouldn't do. Why is this? Because from all of what we said, what do we expect? We said that the volumes of the basin of attraction were multiplicative, and that the probability of a volume of a basin of attraction went like E to a certain function of log V over N. So we said that this was going to be a scaling function, okay? And then we also said that the number of states also, for example, of a given energy goes like, I use lowercase by which I mean energy density, goes like a function that is also exponential. So if I'm going to calculate, so this is number of states, of minima. Now let me look at these. So the basins of attraction of each one are like this. But now, if I calculate the probability of having a basin of attraction of a given volume times the number of guys that I have at that energy, I'm only working at an energy density here. And then I multiply by the actual volume so that I get the total basin of attraction for landing at this energy density. This is a total probability that I land at such an energy density. The probability of a volume of a given energy density, which, as I said, I could do this restricted and it would be exponential, the number of states of that energy density, and then the actual volume of each one. So this is the total volume of initial conditions that will land at that energy. But now we discover that the three of these quantities are distributed exponentially with an n in front. So this is going to be e to the something. This could be dependent on the energy, so it's going to have an n, and there's going to be a smooth function of the energy. And then here, the number of states is going to be also of the same scaling form. And then this is going to be simply the log of v over n times n. But what does this tell me? This tells me that this is the classical thing that has an n in front and a smooth function here. So it will be dominated by only one value. So what does it mean? That this drawing does not apply. What happens is that if I start randomly, I am going to typically go to only one, plus and minus small deviations. I'm going to go to typically one same energy, whatever I do. And this is only by virtue of having assumed that everything is separately exponential. So you end up by saying, just exactly with the same argument that you say that of all the configurations a gas can have, only those that have a given energy density dominate at a given temperature, just exactly the same argument of simply having an exponential number of things that are distributed exponentially with a law like this, then by mere concentration you get that you always go to the same place. No, sorry, not to the same place, to the same energy density. So when you repeat the experiment, our initial objection, who's going to do a theory of out of equilibrium if it's such a mad thing where nothing is reproducible? Not at all. What you should expect is that if things scale properly, everything is reproducible up to square roots of n that you will have in any thermodynamical problem. So is this, and this is very important because it means that when you write a theory for this, you have some hope, of course not always, but of obtaining reproducible results. Okay? And now the last of the last. Okay, the last of the last, and tomorrow I'm going to start with the exceptions to all these rules I gave. But let us consider another problem, a dynamical problem now. So I am going to use heavily the domain growth as an example. Okay, so think of this one. Okay, you all see it? Okay, so now we want to calculate the correlation function at 2 times t prime. So you have two pictures, the two I showed. This one has smallish domains, this one has largish domains, and this is, by definition, so in my pictures, this is black, black, plus white, white, I'm putting the pictures one on top of the other, minus black, white, minus white, black. Okay? Of these two pictures. Okay? Okay. Is this quantity self-averaging, yes or not? Meaning that I do the experiment twice. Do I expect to get at times 1 hour and 3 hours exactly the same result or not? Okay? So what do I have to reason? Well, as usual, but now you cut the system. So let me cut a little piece and a little piece. And more or less you see that statistically this with this is going to be more or less like this with this statistically, you know? Another little piece, and the same as this with this. So I am adding many things that give more or less the same result individually and are, well, a bit independent, no? Like all the things that I have discussed. So, you see my argument, it's a bit cheap, but so the morals of this is that, oh, I didn't tell you that this thing has a T1 that is proportional to its length square when the first domain conquers the entire, so it's later than here. And then it has a T equilibration where the entire system, if it's at finite temperature, can flip from black to white. This takes very long. You need that you're in black and then a white droplet is born, and for reasons of chance it grows and puff, you go to the other, okay? So it's this global, this exists, even in real life it exists, but you have to be very small because otherwise the probability. So this one goes like e to the some power of the length, so it's really a very long time. If you are at times, why is this true? Because what we know is that the typical size of these domains, and this is true also of the Berlin-Katz model, the length of the domain typically grow on average like t to the 1/2. So when this happens, t to the 1/2 is of the order of L, then one has conquered, okay? Now, so the argument I gave here shows you that when this number is much smaller than L, then I can break the system into independent pieces and consider that this is the sum of throwing a coin many times and it concentrates on something. So this is a non-fluctuating quantity when the times are smallish, but still for an infinite system forever and ever. Is this clear? On the other hand, if I consider very long times that diverge with L but more seriously, what happens? My system started from zero magnetization, because zero, here it's black minus white. So it starts from zero magnetization, but at a certain time, which is of the order of the conquering of the domain, it becomes close to 1. Actually, a number like this. This first time is the conquering time. T is L squared. And then at a very, very much longer time, the system will flip Poissonianly, because it's a random stochastic process, will flip between black and white. But these times are gigantic, okay? But now if I do the correlation function between two times that are here and are separate this way, you see that no longer I can assume that the thing concentrates at all. So the correlation is no longer a non-fluctuating quantity. And this is a very, very important thing because it has to do that when you do dynamics in times that are short, everything is self-averaging. Then there comes a time when and the fluctuations grow. Why do they grow? Because at longer times you have less independent parts. So you're adding less things. And this for concentration of measure is bad. Okay? So the fluctuations grow but stay put until you reach a time where the whole thing breaks its neck, and all times that are longer, you no longer. So what happens is that here, with times like this, c squared average over the experiment minus c squared, this is big. So, and I conclude with a remark that this is extremely general. It is true for spin glasses, but it is more than that. It is true for algorithms. So with Florent, who's there at the back, we did a coloring problem where we used Woksat, which I actually don't quite remember what it was, but and the number of errors goes down in a perfectly reproducible way. And if the system were infinite, it goes there. It doesn't go to zero because we placed ourselves in a difficult part, but there are solutions with zero. Let me put 0 here. So it goes to, but then if the system is finite, occasionally, just by chance, because there is randomness, it can hop up to here and hit 0. Once it hits 0, the program stops. So it is perfectly deterministic. If n is infinity, and if n is finite, you get a process like this one that kills the process. For you, it's good because it means that you manage to solve your problem. It's exactly like the kind of thing we have here, but of course nobody does, I think, this kind of calculations, as far as I know, in algorithmic world. So with this, I conclude.
All your dynamics
Non, il y a 7 inscrits, donc on s'attend à limite avec que 6.
It doesn't change almost anything.
Qui viendra de nous prendre
If you don't do anything very sophisticated,
Mais il y a
or if you do, you do Swensen Wang or something really very sophisticated, I think that you get something similar, but at an incredibly faster. But that's close to a critical point. For here, we're very low in temperature. I don't know if Swensen Wang is.
for person one and because this is just to the icing, right? For
Yeah.
person one, you don't have critical slowing down, so you don't have the L square scaling.
No, you do, because this is not at the critical point. This is the growth of domains. This is a very low temperature. It's a different. It's a different form of. Not critical.
Okay, so if there are no other questions, please do not forget that we have a seminar at 8:30 by Johan Luna. After, we will have cider together at the bar.